Welcome to part 6 of this series of presentations about how to convert aldehydes into secondary alcohols. This video is about the stoichiometric in situ generation of ionic enolates, that is, enolates with lithium, sodium, potassium, magnesium and related cations, and their addition to aldehydes. This strategy of performing aldol additions became possible with the discovery of lithium dialkylamide bases, such as LDA, in 1950, and has enjoyed great popularity since then, in particular in academic laboratories and for the synthesis of structurally complex organic compounds. These strong bases are much less nucleophilic than sodium amide and enabled chemists for the first time to deprotonate ketones, esters and other CH acidic compounds quantitatively and in the absence of competing nucleophiles. Both LDA and diisopropylamine are weak nucleophiles only and generally do not compete with enolates for a given electrophile. Alkali hydrides can unfortunately not be used to prepare alkali enolates from simple ketones. The small size of hydride causes the ions in solid ionic hydrides to be very close to each other, and the resulting high lattice energy of ionic hydrides renders them insoluble in most solvents. Moreover, hydride, being approximately as small as fluoride, has an extremely high charge density. The strong electric field on the van der Waals surface of hydride firmly binds several layers of solvent molecules when dissolved. This lowers the reactivity of ionic hydrides, which can therefore only be used for exceedingly fast reactions. This would be, for instance, the deprotonation of alcohols, which proceeds about 1 million times faster than the deprotonation of ketones. As a first approximation, the pKa can be viewed as the pH at which a given compound will be 50% deprotonated. A comparison of various pKa values of CH acidic compounds shows that LDA with a pKa of 36 should be able to deprotonate any enolizable ketone, aldehyde, carboxylic ester, nitrile and even most NN-dialkylamides. Although sodium amide, potassium terzbutoxide and sodium hydroxide are also sufficiently basic, their high nucleophilicity can cause problems, such as C-C bond cleavage of ketones or the saponification or transesterification of carboxylic acid derivatives. Other synthetically useful bases are the salts of bis-trimethylsilylamine. These are not as basic as LDA, but still basic enough to prepare ketone enolates. The main advantages of the stoichiometric generation of ionic enolates, followed by their reaction with aldehydes, are the mild reaction conditions and few side reactions usually seen. High yields are often obtained, and aldol additions often proceed with high stereoselectivity. The main disadvantages are the need of anhydrous solvents, mostly THF, and low temperatures. To prevent their precipitation, some enolates must be prepared in high dilution, and most bases are expensive. Finally, aldol addition products that can eliminate water are usually rather sensitive and must be handled with care. This is an interesting example of aldol addition of a lithium enolate formed from a cyclopropano-cyclohexanone. The methylene group between the cyclopropane ring and the carbonyl group is more acidic because of the increased P character of cyclopropane carbon atoms, and the lithium enolate was formed with high regioselectivity. An enantiomerically pure but very acidic and configurationally labile aldehyde was added to the ketone enolate at low temperature, and the expected product was obtained with high diastereoselectivity and without racemization. In this example, acrolein was added to the lithium enolate of 1-tetralone. Despite the high electrophilicity and good steric accessibility of carbon-3 in acrolein, a clean 1,2 addition occurred. Ketone enolates can also be prepared from 2 haloalkanols by hydrogen halide elimination, as shown here. The fluorinated enolate added to propanal in the expected way and yielded a fluorinated secondary alcohol. Fluorinated ketones are highly electrophilic and tend to form stable hemiacetals or hydrates, as was the case here. Unlike titanium and some silicon enolates, alkali enolates cannot usually be formed with high stereoselectivity from most ketones. In this example, a 7-to-3 mixture of E and Z enolate was formed, despite the low temperature. Accordingly, a mixture of diastereomers was obtained upon reaction with benzaldehyde. With this sterically more demanding ketone, however, both enolate formation and aldol addition proceeded with high diastereoselectivity. The stereochemical outcome can be rationalized by steric repulsion from the bulky terz-butyl group. First, the less sterically crowded enolate was formed, and in the closed 6-member transition state of the aldol addition, repulsion between the phenyl and the terz-butyl group led to the almost exclusive formation of the syn-aldol product. Carboxylates with alpha hydrogen can be deprotonated a second time to yield reactive enolates. Without any additive, butyl lithium would add to the lithium carboxylate and convert it into a ketone. But in the presence of secondary amines, these are deprotonated much faster. Here, one of the two diastereomeric aldol addition products was even formed with relatively high enantioselectivity, despite the lack of any covalent bond between the chiral auxiliary and the enolate or aldehyde. The authors proposed that the high enantioselectivity was the result of the formation of mixed aggregates between the lithiated diamine and the enolate. In this example, again a chiral enantiomerically pure lithiated amine was used as base. Because the ketone had two pairs of diastereotopic protons, the chiral base generated an enantiomerically enriched enolate, which reacted with heptanal to yield mainly one diastereomer with high enantiomeric excess. So, what are the typical side reactions? In the presence of bases, aldehydes sometimes disproportionate into acids and alcohols, in the so-called Cannizzaro reaction, or into esters, the so-called Tishenko reaction. Therefore, when using strong bases to promote aldol additions, some hydride transfers may also occur and yield unexpected esters of 1,3-diols or the unesterified 1,3-diols. Enantioselective versions of this reaction have also been reported in the given references. Further potential side reactions include the elimination of water from the products to yield olefins. Because the initial product of these reactions is an alkali alcoholate, and because alkali oxides are poor leaving groups, elimination is much less frequent when using stoichiometric enolates than with catalytic enolate formation. The low reaction temperature also helps to prevent elimination reactions. Another side reaction occasionally seen is the oxidation of the produced secondary alcohol by an excess of aldehyde to a ketone. Some alpha-beta unsaturated aldehydes may also undergo Michael addition, in particular in the presence of traces of transition metals, such as copper or palladium. Finally, steric crowding in some enolates or aldehydes may slow down the C-C bond forming reaction so much that deprotonation of the aldehyde by the enolate becomes dominant. This can be prevented by using less basic enolates, such as titanium, boron or silicon enolates, which are discussed in other videos. Here's a small selection of some further examples, but many more have been reported. This chemistry is also used for large-scale preparations, where the biggest challenges are usually the low temperature, the stability of the intermediates, and the recovery of THF. The next video will be about the less basic boron enolates. See you then.